All right. Hi, everyone. I'm Hitaishi, and today I'll be presenting a paper called Agent Orchestra. So it's about building multi-agent AI systems that can handle real-world and complex tasks. The core contribution is something called the T protocol, and the system is built on top of it, and it achieves state-of-the-art results on some pretty challenging benchmarks. So let's get into that. So, before we talk about what this paper does, let's talk about why it was needed. Uh, most existing agent frameworks like Google's A2A and Anthropic's MCP have the same fundamental problems. First, there is no unified way to manage the life cycle of your components. Your prompts, tools, and environments are all handled separately with no shared structure. Second, everything is static. Once you define your agents, they don't really improve. There's no feedback loop. And third, environments like a web browser or a file system aren't treated as proper managed components. They're just bolted on with some custom glue code, and that glue code breaks every time you change anything. So these basically aren't just minor inconveniences. They also prevent these systems from scaling to real tasks. All right, next, the task description. So, what is the problem that the paper is actually solving? The task is general purpose and long horizon problem solving. So, things like multi step web search and reasoning over PDFs, audio and video, executing and debugging code, and also things like cross referencing spreadsheets and XML, all in a single run. So, what makes this actually hard is that there is no single agent that can hold all the tools needed for this. Context has to persist across many steps without falling apart. Um, so you might hit a subproblem in the middle of the task that requires a tool that doesn't even exist yet. And the benchmarks that they are evaluated on, especially HLE, requires expert level reasoning. Um, so yeah, that's what the task description is. Yeah, let's get into the T protocol. The paper's central proposal is the T protocol: tool, environment, and agent. The idea is to treat all three as first class components with explicit life cycles, versioning, and a shared management layer. So here, TCP handles the tools. Everything is versioned, systematically searchable, and managed throughout its full life cycle. ECP handles environment. It formalizes things like web browsers and file systems with proper observation and action spaces, so they are isolated and reusable. And ACP handles agents. It captures their roles, capabilities, and coordination patterns in a structured way. So the key insight here, and this is what sets T apart, is that the boundary between these three are fluid. Um, an agent can be packaged as a tool. A set of tools can be elevated into an environment, and an environment can gain reasoning capabilities and become an agent. So T basically defines 6 bidirectional transformations to make this work cleanly. And on top of everything, it is versioned and traceable. So every run is linked to the exact component versions used. And this makes debugging and reproducing results actually more feasible. So let me just show you a figure that's used in the paper. Yeah, this is what I was just talking about. So you can have a look at this as well. Right. So this is basically how T compares to A2A and MCP side by side. And I think it's pretty clear that T is the only one with life cycle management, self evolution support, entity transformation, and proper context management. The scalability difference here is also very significant. T achieves big O of log n, coordination cost versus big O of n squared for A to A's flat peer-to-peer model. Yeah, so about the transformations, let me just spend a moment on the 6 transformations because they're one of the paper's core novelties. A to T packages an agent's capability as as a reusable tool. So a deep research workflow becomes a single callback function, callable function. T2A does the reverse and it makes the tools the actuators of an agent's reasoning. T2E takes a collection of tools and it elevates them into a stateful environment, like combining code edit and debugging into a single programming workspace. Um, A2E basically encapsulates an agent as an environment, and it's useful for things like market simulation. And finally, E2A adds reasoning to an environment so that it can act as an adaptable opponent or partner. Next, we have self-evolution. So this is one of the more interesting parts. Agent Orchestra can actually improve itself during execution without requiring fine-tuning by the underlying LLM. So the loop basically works like this. A task runs, the tracer records everything, failure points are identified, and then either text grad or self reflection generates targeted edits to the component that caused the issue, which could be a prompt or a tool code or agent logic. So the updated component is registered as a new version, and the old versions are preserved so you can always roll back. So what gets evolved here? It can be prompts, tool code, agent code, memory strategies, and successful execution solutions. And this can be reused as templates. The key thing is that the whole thing is versioned and it's not randomly patching things. So every change is linked to something, a version. So next, this is the full system architecture that's provided in the paper. This is what we have discussed until now. And I have a simplified version of this diagram on the next slide. So I'll explain with this. So this is the full system. At the top, we have the planning agent, which receives the user's goal. And this is decomposed into subtasks. It routes these tasks to 5 specialized sub-agents: the researcher, browser, analyzer, tool generator, and reporter. Underneath all of this sits the 3 core protocols we discussed earlier: ACP, TCP, and ECP. And below that is the basic managers, which handle the model access, memory, versioning, and tracing. So the critical architectural insight here is that the planner never sees the full tool pool. It routes to a domain agent, and the agent only exposes the tools relevant to its domain. This is what gives big O of log n scalability, because every routing decision is local and it's not global. So yeah, coming to the sub-agents, each sub-agent has a specific job. The deep researcher runs parallel searches across multiple engines and keeps going until it has a complete answer. Then we have the browser use agent, which handles real web interaction at the DOM and pixel level. Um, the deep analyzer, which handles any file type, if it's PDF, audio, video, zip, anything, with type specific strategies. The tool generator, and this is particularly interesting, it searches for an existing tool first, and if nothing fits it, it generates a new code, tests it, and registers it. And the reporter aggregates everything into a cited MD file. So that's about the specialized subagents. Now let me just walk through a concrete example. So the task is this. if Kip ran at his marathon pace, how many thousand hours uh, to reach the moon at minimum perigee? Um, so the planning agent breaks it into 5 steps. The browser agent fetches Kip's record from Wikipedia. Um, I think it's 2 hours, and it gives a speed of about 21 uh, kilometers per hour. The second browser call gets the minimum distance, which is about, I think, 356,000 kilometers. The deep analyzer performs the calculation, and it gets about 16.8 thousand hours, which is rounded to 17,000 hours. The planning agent then verifies it and marks the task as complete. So the final answer we get is 17. What this basically shows is the core loop. The planner routes, the browser then retrieves, analyzer computes, and the planner verifies. So all of it happens with state persisting across every step. Next, we have evaluation. Three benchmarks are used. Gaia tests real world reasoning and tool use across 3 difficulty levels. Simple QA tests short form factual accuracy, and HLE, which is humanities last exam, uh, is the hardest of the three, and it requires expert level synthesis across domains. All use pass at 1, which means the top prediction has to be completely correct, and these are the values obtained. So the results, 89% on Gaia, beating the next best by nearly 2 percentage points. And we have 95.3% on simple QA, which is above perplexity deep research. And we have 37.46 on HLE, which is a pretty massive jump over OpenAI's deep research at 26%. So these are a bit more than marginal improvements, I would say, and they are consistent across all 3 benchmarks, which means that the architecture is actually doing something novel and different and better. Yeah, coming to ablation. So the ablation study is also worth looking at. The planner alone gets 36.5%. Um, Adding the researcher increases that by 56%. So that is the single biggest gain across the whole table. Adding the browser also nearly doubles performance again. The analyzer again adds 8%, and the tool generator adds about 12% on top of that. So the key takeaway from all this is that no single uh, agent is performing as well as the combination is. And the tool generator's contribution is also specifically telling. It proves that a fixed set of tools will always hit a ceiling, as opposed to like a tool that can be generated on that instance. So right. Yeah. Coming to the self-evaluation results. Using self-reflection on GPT 4.1 bumps the AIME 25 accuracy from 20 to 33%. So that is about a 67% relative gain. GPQA Diamond goes up about 11.6%, and the tool reuse rate of 30% across 50 plus generated tools shows that the system is building a useful toolkit rather than regenerating the same things from scratch. Okay, coming to baseline comparisons. So there are 4 baselines and 4 different failure modes. Um, O3 with no tools hallucinates because it's relying on parametric memory, so it can't verify anything live. Perplexity Deep Research is a strong retrieval system, but the same model proposes and validates hypothesis, which introduces confirmation bias as well. Um, a world is a flat multi-agent system. Its planner sees the entire tool pool at once, which causes context explosion at scale. And Langfun hits a capability ceiling because it can't generate new tools on demand. Agent Orchestra kind of addresses each of these specifically, and it performs decoupled retrieval and analysis, hierarchical routing, and on demand tool synthesis as well. So, yeah, we're moving towards challenges and error cases now. So the paper is quite frank about where it fails. The visual grounding problem is one of the main ones, and the system counted six errors in episode select instead of four, because sorry, six E's, which is the error instead of four, because a language understanding doesn't translate to pixel level precision. Cost and latency are a genuine issue for complex tasks as well. Um, 10 minutes and 100K tokens is too slow for anything that is interactive. Um, the system also amplifies LLM errors rather than catching them, which means that a bad base model makes everything downstream worse. And the three protocol architecture is a real barrier to adoption because it takes significant effort to learn compared to just writing custom code. Yeah, coming to the conclusion. To wrap up, T basically gives you a unified lifecycle management, versioning, and fluid role boundaries across tools, environments, and agents. T. Agent Orchestra, which is built on the T protocol, hits state of the art results on Gaia, Simple, QA, and HLE. The two architectural bets that pay off are hierarchical routing for scalability and self evolution for continuous improvement without retraining. So that is pretty much a summary of what we discussed. And about future work, it includes RL based policy optimization, better video reasoning, and extending self evolution to the communication protocol between the agents themselves. So that's about it. Thank you.